Okay, welcome back for just a quick introduction into the homework assignment. This is to hopefully bridge the previous video about regulation and get us psyched up, hopefully, for the homework assignment, where we'll be able to play with a simulation tool that really allows us to display the response to all sorts of interventions that we can apply through this computer software interface. I want to remind everybody of the core equations that we're dealing with. We saw before this idea of mean arterial pressure being the product of cardiac output, total peripheral resistance. These are parameters that the modeling software will allow you to adjust. And you won't just see mean pressure, you'll actually be able to see pulsing pressure through the different parts of the anatomy. You can also see pressure volume curves. So you can see how the pressure volume loop changes in response to changes in things like cardiac contractility. And we can even change those things on a chamber by chamber basis within the heart. So there's a lot of control here, a lot of fun things we can do. There are some other equations that we also need to keep in mind and that are built into the software, and they have to do with compliance. Now, of course, you will remember that vascular flow is dictated by resistance and pressure and the sort of Ohm's law, but it's also got a capacitive component or a compliant component. And that compliant causes transient changes. Without compliance, when you make a change in one place in the system, that change is immediately executed through the rest of the system. But with compliance, we get vasodilation locally, where there's, let's say, a pressure increase, and then a relaxation or an elastic recoil that happens after that. So that's the compliance aspect from a physics perspective. And then, of course, we have conservation. All good physics systems have conservation. And here we have conservation of volume. So the volume has to be conserved in a closed system, but it can be moved around, right? It's constantly being moved around because the heart's pushing it. And that creates a time-dependent flow pressure situation where the compliance plays a role, and all these things, come together. So it's just good to keep in mind that any change or difference in the input flow compared to the output flow over some period of time will cause the volume to change. That simply says if there's more flowing into a chamber or more flowing into a segment of vessel than there is flowing out, then of course, over time, the volume has to increase. And it increases to an extent that is dictated by the compliance. And so this is where it all comes together, and that compliance also we can use to calculate the resulting pressure that will arise from a change in the volume brought about by more flow going in than going out. And that's how conservation really plays out in mathematical terms. The other, we didn't get into equations of this, but you can picture the equations that would be behind this. We have a control system, and control systems, of course, they do things like compare. So that's a compare operation. They have a negative feedback system. So that means that some value is being amplified and inverted. So, and that inversion or that amplification is happening as a function of the difference between some set point value and the actual measured value. So those all naturally lead to mathematical equations and functions. And there's a whole, electrical engineering has whole courses on this topic of control, mechanical engineering as well. So there's lots you can study and learn about control systems generically. And so there's equations that are embedded or that come out of that are embedded in the software. And then finally, there's a really simple model that we can think about that really describes how the overall blood moves through the body. So here's a situation in 4 panels, and you can zoom in on these and have a look at them. But this is the scenario at rest initially, and then when suddenly the heart stops beating, for example, and the steps that arise as a function of that with the way the parameters change, and there's text at the bottom that sort of explains the steps here. And so this is at a high level what you can picture the response of the cardiovascular system being to something as dramatic as the heart not beating anymore. And so that's a very crude model. It is almost qualitative. It's not really a quantitative model. But instead, for us to really focus on, we have a piece of software called CircAdapt. Now, CircAdapt comes from the University of Maastricht, which is in the Netherlands. I'm sure you all know that, right? And it's a lovely part of the Netherlands. If you ever get a chance, go there. It's surrounded by Belgium and France and Germany, so it's really sitting way, a long way away from Amsterdam. But there's a fantastic group of physiologists here who do a lot of modeling and a lot of research. And out of their understanding of the regulatory systems in the cardiovascular system, they implemented this software, and it's freely available. The homework will give you a link to where you can download it and instructions on what to do. So hopefully, you're a little motivated after hearing the way the regulatory system works and appreciating at least some of the math that's behind it and some of the equations in physics. You'll be a little bit motivated to play with this tool and see how your cardiovascular system, because it is meant to mimic a human system, how our cardiovascular systems respond to big and little changes that you can make with this software. You can subtly change contractility or subtly change heart rate and see what changes then arise in the mechanical or hemodynamic behavior of the heart, and in the pressure volume loops, in the flow, in the pressure tracings. You can see all that interactively with this program. So that hopefully will get you started, motivated. Go grab that software, have a look at the assignment, and let's see what we can learn about our systems by using this modeling tool. Good. Thanks for your attention. See you soon.